Video, we're going to be looking at vector product or cross product. Well, just bear it in mind, everything we're going to be talking about is related to the right hand rule, right? So let's just dive into it. Vector product is commonly known as the cross product. So while the dot product gives you a single number, which is a scalar, the cross product results in a completely new vector that is perpendicular to the old original vector. So this is what I'm talking about right here. We have for instance, we have a vector A and we have a vector B. So the product of these two vectors is going to give us a new vector which is perpendicular to A and B, which is this line you see right here. Is perpendicular to A and B. So the product of this and this is this. So our new result is now a new vector. So now we have a vector A and we're doing a cross product with vector B. We can write this as the magnitude of vector A by the magnitude of vector B sine the angle between, that is this angle right here, the angle between vector A and B, AB, all multiplied by a new unit vector, that is this new unit vector. Some points right here. So let's start off with magnitude. So the strength is determined by the sine of the angle between them. Let's come back here to the graph. As you can see here, there's an angle between vector A and vector B. And this angle right here, theta, we can see that the greater the angle between vector A and B, the greater the strength. The smaller the angle, the smaller the strength. So let's say the sine angle is 0. We'll see that when we punch in sine 0 in our calculator, we have 0. Because there's no angle between them, so it's 0. So the greater the angle, the greater the strength of the vector. So let's talk about the direction. Now the direction that I'm talking about here is the new unit vector found. So the new unit vector is perpendicular to the plane containing A and B. So this is A, this is B, and this right here is perpendicular to A and B. So our new unit vector is right here because this is perpendicular to A and B. So there are key property to the cross product. Let's talk about the geometric interpretation. The magnitude of the cross product A and B, let me write it right here. The magnitude of the products A and B is exactly equal to the area of the parallelogram formed by the vectors A and B. So the magnitude of this is equal to the area of the parallelogram. So the area right here is equal to this. Right, so we have key points to make, more key points to make here. So in the cross product, it is anti-commutative. It's anti-commutative. What I mean here is that let's say we have vector A cross product vector B. So now we can't just write it's not equal to vector B by vector A. It's not equal. To write this now, the sign has to change. So it's now something more like negative this by this. So it's anti-commutative. You can just change the position. And the next thing to make here is that the cross product is distributive. Let's also have A vector A times vector B plus C. What I mean here is that what I mean by it's distributive is that we can multiply this by this and this by this. So we could have vector A times vector B, right? Plus vector A times vector C. See, this is commutative. On that point, I'm going to make here is that it is not associative. What do I mean by that? Is that let's all have vector A times B times C. What I mean by it's not associative here is that this is not equal to us saying vector A times B, all in parentheses, times vector C. It's not associative. Well, the next point now is that vector product of two parallel vector is 0. What do I mean by parallel vectors is that, let's come back to the graph here. If we have two vectors that are parallel in the cross product, what does that mean is that they are at angle 0 to each other. They keep like they're not touching each other to infinity, right? That is they're parallel to each other. So we can see here that let's say we have vector A cross product vector B, and from the formula that I said earlier, that is the magnitude of A by the magnitude of B sine the angle between them that is between A and B multiplied by the new um the new angle formed, sorry, the new direction. So we can see here that if theta is equal to 0, that is if they are parallel, that is if theta is equal to 0. What I mean by parallel vector is that is 0, right? So if theta here is 0, that is sine 0, we can see that sine 0 is 0, and 0 multiplied by the whole of this is equal to 0. So vector product of two parallel vectors, vector product of two parallel vectors is 0. Yeah. Now um, let's talk about the property of the direction, that's of the unit vector, the perpendicular unit vector. Let's just know that if we have um, a unit vector multiplied by a unit vector, we should know that this is equal to the unit vector on the other axis, and it's also equal to the unit vector on the z-axis, and they're all equal to 0. And okay, let's say we have uh, a unit vector x multiplied by a unit vector y. So because these two are perpendicular to each other, meaning they are at angle 90, they are perpendicular, meaning they are at angle 90 to each other, right? So now we know that sine 90 is equal to 1. So therefore, the sine angle of this times the perpendicular angle, which is equal to 90, the sine and sine 90 is equal to 1. And the 1 found right here, since I said it's perpendicular to either to x and y, we can say that this is az, the new that's the angle, direction, sorry. So this is forming a new direction, a new unit vector, which is perpendicular to this and this. So this is 1 a z. Let's call this the z axis. So this multiplied by the unit vector here multiplied by the unit vector here is equal to this new unit vector. So talking about the new unit vector, I would like to make some points here. If we have a unit vector on the y-axis times a unit vector on the z-axis, this should be equal to a new unit vector on the x-axis. If we have on the z multiplied by on the x, we should have a new unit vector on the y-axis. And if we should have on the y-axis times on the z-axis, we should have a negative on the z-axis, If we should have on the z-axis multiplied by on the y-axis, we should have a negative on the x-axis, and if we should have on the x-axis multiplied by on the z-axis, we should have a negative on the y-axis. Let me show you a simple way of understanding this. Let's say we have a simple way of understanding this is by forming the pattern cycle to understand this, which is, so we have this x to this y to the unit vector z. So you can see here that, okay, I didn't add this up. If we should have on the x-axis times on the y-axis, we should have on the z-axis. So this is the pattern right here. You can see that ax times ay, we have az, ax times ay, we have az, right? So we're moving, which is giving us a positive answer. If we should have ay, this is this, and az, we should have ax. Let me draw an arrow here. You see, we're coming back, so it's still positive. So if we should have ay and az, ay and az, what I write here? Sorry, this should be x here. It should be x. So if we should have ay and ax, you see, this is now going back against the arrow here. So that's why we have a negative az. And if we have az right here and ay, you see that we're going back. That's why we have a negative ax. And if we have ax and ay, you see we're going back against the arrow. That's why I have a negative ay. Now, just for the sake of understanding this whole thing, let's make an illustration. Let's say we have ax here, right? We have an arrow pointing to ay. I'll have an arrow pointing to az. I'll have arrow pointing back to x. So let's have our az here. Let's have our ax here. And let's have our ay here. So you can see that ax multiplied by ay, we have a positive az. Ay multiplied by az, we have a positive ax. Az multiplied by ax here, we have positive ay. So you can just always visualize this in your head whenever you are solving a problem. So now let's talk about the determinant method of the cross product. So let's say if we have a unit vector A, we have its value plus we have a unit vector Y, and um we have this, and we have a second vector B. Right. Okay. And we're meant to find the cross product, and we're using the determinant method. So forming our tree, our by tree grid, we first of all put our unit vector on top, right? So we have our AX, BX, AY, BY, and AZ, BZ. So we can use the determinant method to find this, to find our um unit vector. So let's talk about the projection of a vector on another vector. Let me just draw this out. Right. So I'll have a vector A, I'll have vector B. This is in the B direction, right? This theta here is theta AB. So let's say, let's start with the scalar component. So let's say scalar component of vector A along B is called projection of A on vector B, and is given by AB equal to A cos theta AB. The projection of a vector on that vector, let's just reason it like a shadow. How much of another shadow is covering another shadow, in that way, just for understanding. Right. So how much of vector E in this instance is covering vector B? How much of this shadow is covering the shadow of vector B? Let's just visualize it in that way for understanding, right? So um that is, we can write this as, since we're considering only the magnitude, which is the length, so the magnitude of vector A multiplied by the paths along vector B, right, cos the angle between them, and if the angle, let's say the angle between them is 0, assume 0, right? So cos 0 is equal to 1. So to solve this, we use the formula, that is the vector times, or dot product of the direction along vector B. So if we're asked to find the projection of vector on that vector, the scalar component, we use this formula. And if we're asked to find the vector component of vector A along B, this is just simply the scalar component multiplied by a unit vector along B. So this is the formula for the scalar component. Then for the vector component, we have it as the scalar component, right? We have it as the scalar component multiplied by its unit vector. Okay, that's not clear. Let me just write it up here. The vector components the vector components is equal to the scalar components, right? This is the formula of the scalar component, but in the vector component we multiply it by the unit vector along B.